Welcome to Quantum Photonics. In the rapidly evolving field of quantum information science, the task of certifying that of an n-qubit state synthesized in the lab closely approximates a target state is of paramount importance. Traditional methods for decertification often demand either deeply intricate quantum circuits or an impractically large number of single qubit measurements, making them unsuitable for large scale quantum systems. So, however, there is a groundbreaking study, a research from Caltech, whose main author is our guest speaker, who has introduced a transformative approach. So, we will be hearing his a story about his paper here in Quantum Photonics very shortly. So, if you can check at the link on the chat, on the room chat, that is his paper. You can try to preserve it and read it later on. So, Xin Yuan Huang is a research scientist at Google Quantum AI and a visiting scientist at MIT and an incoming assistant professor of theoretical physics at Caltech. So, he obtained his PhD under the supervision of John Preskill and Thomas Vidic. His research focuses on understanding how the theory of learning can provide new insights into physics, information, and quantum computing. So I also take this opportunity to congratulate Dr. Huang, of course, Professor Huang already, because he is a recipient of the Clauser Prize at Caltech for his PhD thesis, Learning in the Quantum Universe, which was judged to have the greatest potential to open new avenues of human thought and endeavor. And of course, his mentors are so proud of him, as we all are. And I will not take time anymore. I would like to give you Dr. Robert Wang. This is his return to quantum photonics, and we are very excited to hear his talk. Robert, welcome to Quantum Photonics.
Thank you so much for the introduction, and thank you for the congratulations. I was also very happy to receive the Clauser Prize. It was a very big thing for me. And yeah, today I'll be talking about our recent result, which I would say is a fairly mathematical result, but for quantum photonics, I thought I would like to go through this result in a more high level and perhaps a more philosophical um, a way instead of the more mathematical and technical approach. So I'm probably not going to be covering the full slide attached to this Google Drive, but I'll still go through it kind of in a similar order. But a lot of the more technical part of it, I would just be a little bit quicker and just provide some of the high level ideas and insights over the previous intuition on how people think about things and how does our new mathematical proof changes the way people think about quantum entanglements. So let's get started. In the first slide, it's just a title called Certifying Almost All Quantum States with Few Single Qubit Measurement. And this is a joint work with John Preskill and Mehdi Solomanifer. Both of them are currently in Caltech. And now if we move on to the next slide, um, the motivation is very simple and very foundational, which is in order to generate or in order to make quantum information science really a reality, it's very important to be able to manipulate, synthesize, and control quantum systems with very intricate entanglement in the system. It's a very important task for the entirety of quantum information technology. And by creating such a quantum systems, we will be able to achieve beyond classical computation, like quantum computing for solving very hard problems, to sense signals of the outside world better than what we naively can, and also to create quantum networks that allows one to create unbreakable crypto systems, etc. However, if we go on to the, so let's say we go on to the next slide. In order to really achieve such a thing, that is to create quantum systems with very intricate entanglement, and very important thing to do is to check that, in order to certify that, in order to understand if we have really created the desired quantum system in the lab. So before moving on, let's imagine the following setting. Our goal is to design some, or in order to generate some highly intricate, highly entangled quantum state. And that state can be very useful for various downstream tasks. However, because entanglement is a very fragile thing, if there is certain noise in the system, certain error in the process of synthesizing the quantum state, we will not be able to generate the right entanglement structure that we wanted, and hence not be able to get the desired applications um, that we hope for. For example, it is well known now in the community that if there's noise in the system, if the system is being subject to thermal or other kinds of noises, it easily destroys the quantum advantage that we have in building quantum computers. And hence, a very important task that that appears in quantum information technology that maybe some of you might not have heard of is called certification. So, what is certification? So, the next slide we can see the formal mathematical definition, but intuitively it's very simple. It just says in our mind there's a target state that we care about. Mathematically, I read it as psi, but in reality, it's always hard to create the desired state due to all the imperfections, due to all the errors, etc. In reality, what we are going to create is something that might be close to our target state, the state we have in mind, but also might be far. And that state, which is called rho, is the kind of the lab state, the state that's created in reality, not just in our mind. And the goal of certification is to connect the two, to connect the thing in the reality as well as the thing in our mind, to try to say that they're actually close or not by, by essentially analyzing data from the experiments. So oftentimes what people will do is we will try to perform measurements, try to perform experiments on the state created in the lab, rho. And by doing those experiments, we will extract data, which can then allow us to kind of test if from the data, does the outcome tells us that, oh, the state that was created in the real world is actually close to the state that we have in our mind. So psi is the thing we have in our mind, but rho is the thing that's being generated. And certification task is just to test if they're close or not. So if now moving on to the next slide, there have been tons of techniques that were proposed for doing certification, because it's a very important thing to 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 perform in all kinds of experimental setting. We always wanted to check if the thing in the real world is actually close to the thing in our mind. If we're if they're not close, what we should try to do is to either change the real world, so try to do some manipulation or some control to make it closer to what we have in our mind, or change the model in our mind so that it's closer to what's happening in reality. We do that all the time. And it's the same in the development of quantum technology. However, in quantum technology, there's a very important difference, which is in order to make quantum technology works, we need to generate these very intricate, highly entangled quantum mini-body systems. And at the same time, we know that these entanglements, they're not they're not just out there. They're not just um, physically present, so we can just see them. They're kind of hidden properties, telling us how different individual constituents are actually connected in a very fundamental level. And hence, it's experimentally very challenging to certify or to see or to check whether the entanglement in the quantum system is close to the entanglement we want them to be, the model in our mind. So even though many techniques have been proposed, none of them were actually very satisfactory, especially in the many-body regime. So in the following slides, if you go through the Google Drive, there are various different approaches that have been proposed in and people have been using them or attempt to use them in practice, such as direct measurement, which says we just try to directly measure what we have in our mind onto the state. But that's not really a good approach because performing direct measurement is as complex as the process of generating the desired target state. Essentially what direct measurement does is if we wanted to create certain type of entanglement, then what we do is we just implement an operation that undo all the entanglement and see if we really undo them. But that's as hard as creating the entanglement. And hence this is not really a good approach. Approach one, which is based on classical shadow, or another way to say it, based on randomized measurements, it also has its own downside. For example, it needs these deep circuit in order to perform this certification task. There are also several other ones. On page 16, you can see approach 3 called cross-entropy benchmarking, which was proposed and used in this very famous paper by Google Quantum AI that demonstrates quantum supremacy, which has now garnered thousands of citations, and it's one of the key milestones in quantum information science. And while it sometimes works in practice, the key challenge is that this approach is heuristic in nature. So it doesn't really rigorously address the certification task. It could be that using this approach, it tells us, oh, we've done a great job in creating the entanglement we want. But actually, the state that was created in the lab was very far from what we have in mind. So it could provide these like false positive in using that approach. So now if we just jump directly to to page 19, basically all of the existing protocols for certification. So another way to think about certification is really this connecting between reality and what we have in mind. All existing approaches either require a deep circuit before doing measurements or require an exponential number of measurements, which are not practical for a larger system, or apply only for certifying some very special state that we have in mind, or it lacks rigorous guarantee. Hence, it's just like some heuristic that sometimes work, but sometimes it just fail. So these are some of the existing challenges from a more technical and kind of mathematical perspective. But on more high level, it's really quite hard to see how we can avoid, how we can get around these challenges. And the reason is the following. So suppose there's many atoms that were sitting there. We wanted to engineer them so that they form certain entanglement structure, some very intricate one, very global ones that connects all of them. And now experimentally friendly approaches are often we just probe each of the atoms individually. We perform some measurement on each of these atoms and try to, from the measurement outcome, try to see what's happening in them. That's more like um, as a classical human being, when we try to access quantum system, that's typically what happens. However, if that's what we are going to do, then it seems impossible to see these global entanglement, because entanglement is a property that is hidden down there. It talks about the correlation between all of them in a very quantum mechanical way. But now if we just probe each of these atoms, we're essentially going to turn the whole system into a classical thing. And hence, through that process, it feels like we shouldn't be able to peek at the underlying complex and intricate entanglement structure. And hence it raises the following question posed in page 24, which asks, can we rigorously certify, or when we see certify, we can think about it as see, can we rigorously see highly entangled quantum states by performing only few single qubit measurement? So single qubit measurement is just a jargon that means we probe each of the constituent, like each atom in a many body system individually. So intuitively, it feels like the answer to this question should be no, because entanglement is something that's very global. On the other hand, these single qubit measurements are something that's very, very localized. And hence, it feels like when you only probe things locally, one shouldn't be able to see things that are highly global. And furthermore, we can ask an even more ambitious question, which seems even more unreal, which is posed in page 25. That is, can we rigorously certify not just highly entangled quantum state, but almost all quantum state by performing few single qubit measurements? Again, the answer to this question, intuitively, at least from all of the existing results, seems to suggest that the answer to this question is no. But there's also no mathematical proof that says the answer to this question really is no. And what we actually found in this work is that by using a more clever post-processing and by using a different way of thinking about this problem, we can actually prove that the answer to this question is yes, we can actually certify, we can actually see almost all kinds of quantum entanglement by performing only a small amount of single qubit measurements. So the outline of the following talk is given in page 26, which first I'm going to present the theorem. Then in the next part, I will talk about what is the protocol to establish the theorem, and I'm going to end with various applications in the development of quantum information technology. So let's begin with the first theorem. So theorem 1 on page 28 essentially proves the following. It proves the affirmative answer to this open question that I just briefly mentioned earlier. And the theorem statement says that for almost all unqubit state, here the state means the state we have in mind. For almost all unqubit state that we have in mind, we can check if the state that lives in the real world is close to the state we wanted to create, the one we have in mind, using only a number of single qubit measurement that only scales quadratically in the system size. And hence, if we wanted to certify, we wanted to check if the state that was created in the real world, say, is a 100 qubit state, we only need to perform 100 squared number of measurements. Whereas previously, it feels like we need to perform an exponential number of them in order to check the underlying entanglement. Particular, this certification procedure applies to any state that was generated in the real world. Particularly, we can imagine the real world to become very adversarial. They try to hide the error. So they try to be devious in creating a state that's actually very far away from what we have in mind, but somehow I try to um, look like it's close to what we have in mind. And essentially, the theorem says that that's not possible. There's no way for reality to hide the difference, and hence we can always check it efficiently. Whenever there's some error that the reality try to inject into the many body system, we will be able to identify that error. Another surprising aspect about the theorem is that the number of measurements only scales quadratically in system size, even when the state we have in mind has some very, very high complexity. So maybe we have in mind generating some extraordinarily complex quantum system where the entanglement between them um, is exponentially complex. Even for such a situation, a small number of measurement is already enough. And hence, the theorem answers the question that we posed earlier in the affirmative. So in the next slide, I'm going to dive in a little bit more to better understand what's happening inside this theorem. So why can we do that? Why is it true that for almost all state that we have in mind, we can always check if the real world is close to that state in our mind? And that has to do with a mathematical concept called relaxation time. It's actually a very simple concept with that I'm going to explain shortly. So suppose we have a state in my mind, that is the target state psi. So we are now on slide 31. Suppose we choose some basis. So think of it as we choose a configuration to say what are the classical possible states for this many-body system. And now when we measure the quantum system in that basis, it will randomly collapse into one of the classical configuration. So we're going to consider n-qubit state, which means what each of the configuration would just be an n-bit string, n-classical bit, a string of n-classical bit called B. So when we measure the system under this basis, then we're going to collapse it into a bit string B. It will be a random bit string that pops out according to some distribution, which is this measurement distribution, which we call pi of b. So pi of b is just a probability that we see the bit string b. And for those of you that are aware, there's a metric structure called Boolean hypercube, which is created in the following way. We consider all of these exponentially many different classical configurations, all the different bit strings, and we connect them, we put an edge between them if the two bit string only differ by one bit. So like 000 is connected to 010, 000 is also connected to 100, etc. One can see the figure in page 31. Now, what we're going to do is we're going to consider, think of it as a person that's random walking in this high-dimensional cube. So that's called a random walk. Let's say the person sits at a particular point on the hypercube. So that's labeled by this diamond, B. Now what happens with this random walk is the person would look at one of its neighbor. Neighbor meaning there's an edge connecting the current point and the other point. So for example, 010 is connected to 000, 110, or 011. It's just going to randomly select one of them. So in page 34, it selects 000. So it's going to be selecting randomly, and hence every time it will be different. But let's say this time we get 000. What would happen is with some probability, according to the measurement distribution, it will stay at the current point, or it would jump. And that's the process. So that's a random walk process. It's just a walk on this high-dimensional space. Every time it would just select one of its neighbor and decide either to jump there or stay. And the notion of relaxation time just means how many random steps does the person has to take in order for the resulting distribution to be kind of close to the measurement distribution. And that's called relaxation time. Basically, just how many points, how many steps does it need to jump to perform this random walk to be constant close to the stationary distribution. And now with this concept of randomly walking on a high dimensional cube, we can essentially state theorem 2, which is on page 37. It says that for any state, any n-qubit state, psi, state that we have in mind, that we wanted to check if the real world actually have generated that state. For any such state with a relaxation time of tau, we will be able to certify if the state in the real world is close to the state in our mind by performing order tau single qubit measurements. And hence it provides a new connection that was previously unknown to us, that the number of measurements required to check the real world, to check if the real world is close to the thing we want, the thing in our mind, is related to this mathematical concept of random walk. Essentially, how fast we can, when we are walking, how fast is like when we start walking on this high-dimensional cube, how fast does it converge to the kind of the final distribution is essentially closely connected to how fast we can check if the state in the real world is close to the state in our mind. So the theorem 2 essentially builds a new connection between two very distinct mathematical concepts of random walk and the sample complexity to perform certification. And from theorem 2, essentially we can establish theorem 1. So even though I'm presented it as theorem 2 and theorem 1 and 2, actually we prove theorem 1 by first proving theorem 2. So after proving theorem 2, what we then show is that for almost all kinds of quantum entanglement structure, the relaxation time is bounded. So if there's an n-qubit state, the relaxation time is bounded by roughly n squared. And hence, we can use n squared single-qubit measurement to check if the real world is close to what we have in mind or far from what we have in mind. And that's essentially theorem 1. And that's the main mathematical or in some way philosophical result of this work, which says that by measuring each qubit individually, we can actually see the underlying entanglement structure. And the reason behind that is because the entanglement structure, like checking entanglement structure, is closely related to walking on a hypercube. And kind of magically, for most quantum system, even very, very complex ones, it's very easy to walk on this high dimensional cube. So let's get back to build some more intuition about this high dimensional cube. Let's go back to slide 33. So note that this high dimensional cube is exponentially large. If there's n bit, then a Boolean hypercube contains 2 to the n different locations or different points that the person could stand on. However, this cube is very well connected. So, for example, if we wanted to go from all 0-bit string to all 1-bit string, we only need to take n jumps. So every different locations, they're always connected by n jumps. So when we view it from this way, when we view it from a Boolean, from this high dimensional cube perspective, different configurations, they're quite well connected. Another way to think about it is, even though there are exponentially many different classical configurations for a quantum state to be in, or it can be a superposition over exponentially different configurations, every pair of configurations can be reached from one to the other by making only n changes, which correspond to n jumps. And as in some way, they're also kind of close. Even though there are exponentially many of them, they're not too far away from one another. And that plays a crucial role in this certification process, in checking whether reality is close to what we have in mind. So after talking about the theorem and some philosophical comments, let's jump to the real world protocol. So in practice, what do we do in order to check if the real world is close to what we have in mind? And that's being discussed on slide 40. It's a very simple procedure, and we just repeat the following for a few times. So here, this quantum state, this green ball, just corresponds to just an illustration of the state that was generated in the real world. What we're going to do is we're just going to measure each of the individual atom or individual qubit in the real world. But we are going to measure them in slightly different bases and in a more structured but at the same time randomized way. And the procedure looks like the following. So first, we're going to pick a random qubit X. Just going to pick one of the atom. And for everything except for the one that we chose, we measure them. We kind of just see what's up with them. We see each of the individual qubit except for qubit x. So we see them in a standard basis. For example, for n qubits, we just check n minus 1 qubits and see what they collapse to. So they were going to collapse to some n minus 1 bit string, and we're just going to see that. And after that, for the qubit that we have chosen randomly, for that single qubit, we're going to measure them in a random basis. So it can be a completely random basis or a random Pauli basis, or known as random X, Y, or Z basis. And yeah, and now we are at page 43. Now if we move on to page 44, we see that that's it. That's the whole protocol. That's everything we do in reality. We take the system. Every time what we do is we just pick one of the qubit. Everything else, we just collapse them. And now for the remaining qubit, we again collapse them, but now collapse them in a random basis, in a randomized fashion. And we just keep repeating this process for a few rounds, and then we get the needed measurement data that allows us to check if the thing happening, if the entangled state in reality is close to the state we want, the state we have in our mind. But how does that processing works? So basically, the process looks like the following. So when we collapse the state, except for the one we chose, except for the qubit that we chose, which is labeled as the blue one, when we collapse everything else except for the blue one, it essentially causes the blue qubit to also change. So that's like the famous structure of entanglement. Whenever we measure everything else, it also causes the one that was entangled with it to change to a certain state. And that's called a post-measurement state. So the post-measurement state on that one qubit that we haven't measured will be proportional to the expression that was shown on 46. Essentially, we can know what they are because we know what is the desired state, we know what's the state in our mind, and we just kind of simulate that process and say, okay, so if the reality is really the same as what we have in our mind, then we will know what's happening, what's going to happen in that one qubit that we haven't measured. It's going to be collapsed. I mean, it's going to, because of the collapse for the rest of the system, it's going to cause that state to change to a certain state. That was written in slide 46. And by performing this randomized basis measurement on the qubit that we've chosen, we can use this formalism called the classical shadow formalism that we developed 4 or 5 years ago to check whether the one qubit state in the real world is close to the one qubit state in our mind. So checking whether a one qubit state in the real world and one qubit state in our mind, that's very easy. And that's what we're doing here. However, we're going to check that in a conditional fashion because we have this collapse of everything else at the beginning. And then we check the closeness of that one qubit state. And that can be done efficiently. But the tricky thing is, how does that relate to closeness in the entire n-qubit system? There's so much entanglement in them. How can we just use the correctness of a single qubit to infer the correctness of the whole system? And that is where random walk somehow comes into play. So now, after averaging out the kind of the measure of closeness, also known as fidelity, after averaging out the fidelity, we will get this quantity called shadow overlap, which will be close to 1 if every time when we do this collapse, the one qubit state that we get out in the real world and the one qubit state we have in our mind are always close. Then it will be close to 1. If they're kind of far away, then the shadow overlap will be smaller than 1, and the smallest number will be 0. So shadow overlap is the number that's between 0 and 1, and if it's close to 1, it means that the one qubit state that we got out is always close. between real world and what we have in my mind. And now jumping to slide 49, the key feature of this shadow overlap is that it actually accurately tracks the closeness in a many-body sense. So there's this fidelity measure, which just measures the closeness between the state in the lab, the state in the real world, and the state in our mind, psi. So the same fidelity will be close to 1 if they match up, and they will be close to 0 if they are very far away. And the key feature of shadow overlap is that it can actually be used as a surrogate for fidelity. If the shadow overlap is close to 1, it means that the fidelity would be close to 1. And if the fidelity is close to 1, then the shadow overlap would also be close to 1. And hence, we can just look at shadow overlap. Is it close to 1 or is it far from 1? If it's far from 1, then we know that the real world and what we have in our mind is very different. The model in our mind is just wrong. But if they're close, then we know that the thing happening in the real world is close to the thing happening in our it's close to the state we want in our mind. But there is a factor, which is this realization time. Basically, the realization time has to be bounded for them to have to be for shadow overlap to accurately track the fidelity. And this realization time is the one that we talked about earlier. So for the more mathematically minded audience, if you would like to better understand this shadow overlap, the explicit formula is given in page 52, where I also presented a few examples for how this fidelity and shadow overlap changes. But basically, the key conclusion is stated in the last line of slide 55, stating that the shadow overlap actually has a more Hamming distance nature compared to fidelity. So fidelity is essentially a very strict thing. It says if one of your constituent in the whole system is wrong, then suddenly the fidelity would just drop from 1 to 0, the worst possible value. However, on the other hand, shadow overlap, because it relies on checking things one by one, checking each qubit one by one, it's much more tolerant. So if one of your qubit is wrong, it would say, oh, your score is 1 minus 1 over n. So it has like a more continuous nature in accounting for score, because only one of your qubit is wrong, so you're not completely wrong. You're mostly correct. It gives a score of 1 minus 1 over n, and only when all of the qubits are completely wrong, then shadow overlap will become much closer to 0. And that's just to provide additional information or additional intuition for this new measure called shadow overlap. And hence, shadow overlap and fidelity, while shadow overlap tracks fidelity, they're not exactly equal. And in many practical considerations, shadow overlap is actually a better quantity because it has a more tolerant nature. It captures, it tells us how many things are going wrong, whereas fidelity would just say you're completely wrong when only one of your qubit is wrong. So now that brings us to the final part of the talk today, which is what are the application? What is the usefulness of certification? So if we just use the word, oh, if we just use the word certification, somehow Siri is telling what the usefulness of certification is, but I'm just going to say it myself. So certification, if we understood it properly, it's just a protocol for checking if the reality really matches with what we had in mind or not. And hence there are actually many ways to use it if we're creative enough. So if we jump to slide 59, the first application is to do benchmarking. That's just kind of by definition. It helps us check if we have really created the right thing in the lab or we have created something completely wrong. So in the following slides, I presented several numerical experiments comparing between this very famous approach called cross-entropy benchmark, or XEB, that was used in quantum supremacy experiment versus shadow overlap. And from there, we can see that for white noise, XCB and shadow overlap both works very well. That's on page 60, 61, 62, 60 and 61. And then if we change to a different noise called coherent noise, meaning that, so white noise means like the state is wrong in a very uniform sense. But now if the state that we have created in the lab is just like the entanglement, it's still a very coherent entangled system. It's a very quantum system, but it's just the entanglement structure is wrong. So it's still very quantum, but the entanglement structure is not what we want. That's what coherent noise meant intuitively. Then we see that XCB start to perform much start to differ from the true value. So here we're in 4-qubit, we see that XCB says the fidelity is actually lower than what the true fidelity actually is. We can also change to different states. So on slide 64 to slide 67, you can see a different situation for some random structure state. So we created some product state and we apply some phases to it. And now again, for white noise, XCB and shadow overlap both performs well, but XCB has a much higher variance, so it needs more experiment in order to converge. But now if we jump to slide 66, where we have this more structured state and also coherent noise, then we suddenly see that XCB is going a little bit haywire. So as the coherent noise increases, as the noise increases, somehow the XCB scores start to increase as well, and actually go above 1, which doesn't really make any sense. On the other hand, for shadow overlap, we see that it gradually decreases and tracking the true fidelity quite well. It doesn't track it perfectly because they're different quantities. They're fundamentally different quantities, but it still track the true fidelity quite well. And similarly, for a bigger system like 20-qubit on slide 67, we see that, again, XCB is overestimating what the fidelity is, meaning that it's not seeing the noise that was presented in the system. On the other hand, shadow overlap does track the noise pretty well and says that, as the real world and our mental world, as the discrepancy between the real world and the mental world start to widen, shadow overlap also says the fidelity would go down. So that's the first application. The second application is related to this very famous line of work called machine learning quantum state tomography, or neural network quantum state tomography. The idea there is to train a neural network, such as a transformers model, or it could just be a simple feed-forward neural network, try to train an ML model to represent the real world. So in this case, the real world is fixed. And whenever there's a discrepancy between the real world and the kind of the model world, in this case, the thing we have in mind is just a neural network. Whenever there's a discrepancy between the real world and the mental world, we will resolve the discrepancy by changing the neural network. So the neural network try to match up with the neural network, with the real world. So the real world is always fixed in this case. This can again be done using this shadow overlap. So we can use shadow overlap to check whether the real world and the neural network model is actually different. If they're different, then we try to drive down, or we try to make the shadow overlap higher and higher by training the weights in the neural nets. So using that, we can train it. And furthermore, there's an important aspect that was missing in the previous literature. So in the previous work, people have also cooked up all kinds of different loss functions to train neural network to represent quantum many-body system. However, a missing component in the previous work is after they train it, maybe the neural network failed. Like maybe the neural network got stuck in some local minima, or maybe the data is just not enough to guarantee that the neural network can learn well. So it starts to hallucinate patterns that were just not present in the real world. And hence, what the neural network thought the world looks like is actually very different from what the real world actually is. And here, by utilizing shadow overlap, which is a method for performing certification, it can also help us certify these heuristic but powerful machine learning models. Essentially, after training, we can then estimate the shadow overlap and check whether it's close to 1. If it's close to 1, it means that the heuristic neural network model is actually close to the real world. And hence, all kinds of predictions or all kinds of properties that we extract from the neural network will be accurate and correct and reliable. Which a priori, when we just train some heuristic model, the prediction might just be completely wrong because it starts to see patterns that were just not there. It hallucinates properties of the quantum system in the lab that were just not present. But with the certification part, it resolved that. And for the next few slides, due to the time constraint, for the next few slides, essentially showcases this for learning some highly complex 120 qubit states. So this is a highly entangled quantum state. And when we randomly initialize it, the system is unentangled. And but the thing in the real world is highly entangled. So initially they are very different. The neural network and the real world is very different. But now we try to train the neural network using the shadow overlap as the loss function. So that's shown in slide 74. So in slide 74, the x-axis is just the number of steps that we use to train it. Initially, the neural network is just kind of wandering around trying to make sense of the pattern in the data. At some point, around 10 to the 5 number of training steps, you realize it catches on to the patterns and it quickly starts to improve. And after that, it converges to the right model. And how do we know that it's the right model? It's because we can test it using shadow overlap. So that's these orange curves where we are reporting the shadow overlap. And we see that as the neural networks start to learn, the shadow overlap also start to increase. And luckily, the shadow overlap increased to a value of 1, meaning that the neural network has really connected to what the real world is. Because when shadow overlap is 1, it says the thing we had in mind, which is now a neural network, is close to the real world. And that establishes this connection. And after establishing this connection, we can now use the neural network for all kinds of purposes, such as to predict what the entanglement structure is and so on. And that's essentially shown in slide 76. In slide 76, we use the trained neural network to predict what is the subsystem purity, which is a way to measure entanglement in the quantum system. And we see that it matches the ground truth very, very well. Up to statistical fluctuation that come from the method that we use to use neural network to predict. So we're using a Monte Carlo method that allows neural network to predict the property, and hence there will be some statistical fluctuation. And that's the only noise that's present, because the shadow overlap and the fidelity of the neural network is very close to 1. Now the final application is in optimizing circuit. So here we switch the role. We have the real world, we have the model in our mind. The model in our mind is now going to be fixed. So there's a target state that we want. And what we were going to do is we're trying to fine tune. We're trying to change the real world, trying to perform circuit, to perform operation, to change the real world such that it generate a state that's close to what we have in mind. So that's the third example. On page 79, we showcase the kind of the landscape when we utilize this fidelity as the metric versus shadow overlap. So especially the difference is particularly sharp for a larger system, so 50 qubit system. That is like the right-hand side figure. We see that when we implement the right sequence of gates to construct the desired state, that's the x-axis, you implement the right sequence of states, of gates. The fidelity keep having a 0, because whenever there's one qubit that's wrong, fidelity you're completely wrong. It's a very strict measure. So when when a metric is very strict, it have this like barren plateau structure. It's always zero until you're very good, and then it starts saying, "Oh, you're great." On the other hand, shadow overlap has a more nicer structure. As you start improving, as you start placing the right gate, it says, "Oh, you're getting closer, you're getting closer, and you're getting closer." So that gives more information to an algorithm to try to optimize and try to create the right state. And hence, on slide 80, we see that if we train using fidelity, which is too strict of a metric, then the training just fell. We're just going to randomly wander in this barren plateau and never hit the right circuit. On the other hand, if we train it using shadow overlap, then it succeeds. And these are the some of the applications that we have come up with, but we believe there are more. So now to conclude, in this work we proved that almost all quantum states can be efficiently certified, meaning that for almost all state that we have in mind, we can efficiently check if the thing in the real world is actually close to what we have in mind or not by performing few very simple single qubit measurements. Of course, the key open question in this work is, can we even prove a stronger thing that says actually not just almost all quantum state, but actually all quantum state can be certified? Or can we figure out some states that cannot be certified using few single qubit measurements? And that's it for my talk. Thank you so much for listening.
Thank you, Robert. And we would like to announce to the audience that we're opening the floor. If you have questions, please raise your hand. We will bring you up the stage. So, here to reset the room, Robert here is talking about his recently, I think it was April, published paper. And he's trying to address the question, can we see highly complex entanglement from a few single qubit measurements? And to reset the room, also, I'd like to introduce him. Um, Xin Yuan Wang, or Robert Wang, is a research scientist at Google Quantum AI, a visiting scientist at MIT, and an incoming assistant professor of theoretical physics at Caltech. He obtained his PhD under the supervision of John Preskill and Thomas Vidic. His research focuses on understanding how the theory of learning can provide new insights into physics, information, and quantum computing. So, I'd like to encourage our audience to raise your hand and ask questions. So, initially, I'd like to ask Robert, how long did it take you to do this study?
Yeah, this actually took quite some time. So a few years ago, I had this idea for essentially the second theorem that connects between this problem of how we can build a relationship between the real world and what we had in mind using simple measurements and a small number of them. So, to the problem of random walk. So, that had been established. But then it's not clear to me whether the relaxation time that I talked about is actually small for any reasonable quantum states. And hence, that part took a while. Um, took a year or two to really figure out what is the relaxation time for, say, almost all state or various specific states, etc. And that really is a mathematically challenging question because it's a well-known problem that bounding mixing time or bounding relaxation time of a random walk for this exponentially large space is typically very complicated. However, we were at the end successful, and that really builds the foundation for this. But then we also spent quite a while, like almost a year, to conduct all these different numerical experiments, to really test it out, to try to better understand how it actually works in practice, and so on. So together, it does took a few years to finish, but yeah, at the end, we're pretty happy.
Thank you. I also noted that I think you had mentioned in your tweet, actually, I noted that you had two reference papers, and one of them, or both of them, you were also an author of as regards shadow overlap.
Yes. So yeah, so in general overlap, important thing that we build on is classical classical shadow. So that's a way to essentially learn some representation of a quantum many-body system, such that we can predict local properties or different kinds of properties about it. Um, however, it, if we focus on single qubit measurement, that is measurements that doesn't require any entanglement, then we are unable to show that we will be able to see this highly global entanglement structure. We can only see properties that are very localized, on only acting on only a few qubits. But so in a way, this result can be seen as a substantial improvement upon our classical shadow framework that was published um, 4 years ago in Nature Physics.
Yeah, thanks, Robert. So, of course, several years ago, I remember about Google AI trying to declare quantum supremacy, and we also note that in order to measure the effectiveness of entanglement, um, you have to check about the quantum volume, also the fidelity, just like you mentioned a while ago, and how long the entanglement lasts. So, any comment on your findings in application to this kind of use case?
Yeah, so that's definitely our main. That's like the starting motivation actually for this work, and that's also the application, the first application that I mentioned on slide 68, which is to perform benchmarking of quantum system to understand how good they are. So I would say so far most of the existing result focuses on benchmarking by looking at like the classical probability distribution and just checking whether that looks good or not, and that only checks like the classical aspect of the quantum system. So if there's a quantum system that we created in the lab, we measure them, it would collapse into some distribution over classical configurations, and people just try to check if the collapse, like after collapsing it, the classical thing that pops out actually looks correct, and that's how people often check, um, often perform benchmarking. But it could be that the real world like this thing we created does have the collapse that looks correct, but the underlying entanglement or the phase structure and so on was just wrong. And hence this result can be essentially seen as an enhancement of that. So when people try to perform like quantum volume tests, in addition to just measuring the bit string outcome, one could also perform this slightly different measurement scheme, which are also as easy or pretty easy as before, um, to also certify the underlying quantum entanglement and the quantum coherence itself, rather than just looking at the classical aspect of it. So, so yeah, so I do, at least I'm part of Google, and I think in future experiments when we try to perform these random circuit sampling, it would be great to report both the XEB score as well as this new metric that we came up in this work, which provides a more rigorous guarantee, in showcasing whether the state that we created in the lab is actually close to the state we wanted to create.
Yeah, thank you. So, today I posted your article, your study in my Facebook groups, which are mostly in quantum physics and also in artificial intelligence. And there's a lot of interest in among the members of the group.
Hmm.
Maybe totally there would be about 500,000 members who are a niche group who are really interested in the fields. And I would like to read some of the questions that they were asking. Perhaps in the near future, you can give a talk about it, especially in the AI community, because every day we would just post common questions or problems that are being addressed about LLMs. But even reinforcement learning and other topics in computer science, we don't talk much about. And your study is very interesting and offers a new insight in trying to correlate different fields. So these are some questions that I got both from the quantum physics groups and also from the AI groups. So there is a question from Roland. Probably you have answered some of it in your explanation earlier, but I would like to ask it anyway, and also for the sake of those who came in late. So, what are the theoretical implications of this protocol for understanding quantum state complexity? Does it offer new insights into the nature of quantum states?
That's a interesting question. So yeah, so for example, in theorem one, so on slide 30, uh, it says that irrespective of the state complexity, this theorem holds. So these states psi can have exponentially high complexity. So the state complexity is extremely large, and yet the number of measurement is just bounded by order n squared. So it tells us, in particular, this is restricted to just performing single-qubit measurement. That is, we check each atom individually. So initially, one might have thought that if we're restricted to just performing measurement on each atom individually, then maybe in order to check, in order to build the equality between the reality and the state we have in mind, if the state we have in mind has extremely high complexity, one might have thought that the number of measurements that we need to perform to check whether the real world is close to the thing we have in mind would also have to be exponential. However, theorem one says that actually it doesn't scale um, linearly or polynomially in the state complexity. The measurement complexity, even when restricted to single qubit measurement, is scales much slower than the state complexity themselves. So that is a very interesting aspect of the theorem, which we're also very unexpecting it. And yeah.
Yeah, thank you, Robert. So, yeah, I think that you should definitely give a talk with this niche group who are specializing in this because they have so much to learn from you. So, it's really very interesting. And Kevin is here. I think he wants to ask questions. But I would just like to ask you, is there a follow-up study on this? Yeah, if I understand correctly, the Google Quantum AI Center is also in Caltech or not?
Uh, yeah. So yes, there are we do have several other ongoing works that try to better understand um, the relationship between learning, complexity, measurements, and so on. So there are actually also some more results coming out. We're still working hard on writing the papers, but we're all very excited about them, and it would be great to give a talk sometime in the future when the papers came out. And to answer your second question about Google Quantum AI, no, actually, Google Quantum AI is in. There are two main locations. One is in Santa Barbara, and one is in Venice. So not the Venice in Italy, but the Venice in LA. So the one in Venice is quite close to Caltech, but it's a different entity. But I should also add, like, there are a few faculties in Caltech that were also like advisor or part-time or were involved in the effort in Google Quantum AI, but we're not co-located. I should also add that actually AWS, so Amazon is they have a building that's just sits right next to Caltech. So AWS also has a actually has a stronger tie to Caltech, but Google is also quite close. It's in Venice, in LA. Um, so together there's quite a nice industry ecosystem near Caltech, like quantum ecosystem.
Yeah, thank you. So I think it's an exciting time to be in Caltech. Of course, it's always exciting to be in
Yeah.
Caltech, but uh, this is becoming more exciting as well
Yes,
because,
particularly
of
from a
course,
quantum technology perspective.
yeah, because you have the facilities. So if you have a theoretical basis, you have you're inspired, you have some intuition. It's good to have an infrastructure, maybe to check if your
Yes,
intuition is correct or not, or
yes.
there are more to learn from. So thank you, Robert. I would like to give the mic now to Kevin, who came on stage. So Kevin, welcome, and I'd like to give the mic to you now.
Oh yeah, hi. Yeah, I got a ex. Speaking of Santa Barbara, yeah, Google Mind, DeepMind. Yeah, I got a ex NASA friend who has a job offer there. They said, but anyways, yeah, I'm a polymath, so yeah, I'm my mind's going all over the place. But maybe I have some general questions. Especially with this. This is yeah, it's my mind's flickering right now. But did you answer this? You know, did what's for as far as quantum state tomography, does this help provide some bounds for to measure the number of independent measurements needed for estimating density matrices? Is one question I can think of.
Yeah. So here I would say so. Oftentimes in quantum state tomography, people try to learn the whole mixed state. So it would be a matrix, but here this result focuses more on pure state. So the thing we have in mind, like, is for pure states. That is, we can establish whether a mixed state in the real world is close to a pure state in our mind or not, that we want or not. So the target pure state. So one can actually use this for quantum state tomography, but it would not be the mixed quantum state tomography, but pure quantum state tomography. So there's also this well-known problem, which is suppose in the real world we have a pure state, then now what we would like to do is to learn that pure state. How can we do that? And essentially this result can be used for that purpose because by with the ability to perform certification, it tells us we can go through all kinds of different state in our mind or different model for states and check which one is close to the real world. And because we have a certification procedure that allows us to do that, we can use this certification procedure to perform learning as well. And that's related to this example two, the application. Um, it focuses on machine learning, but it doesn't have to be machine learning. It could also be tensor network or even just a general vector representation, like a big matrix, like, or a big vector for doing learning. So yeah, so this definitely has application for quantum state tomography, but also note that the general problem of quantum state tomography, um, when the state can be anything, and and yeah, and the problem is well known that there's a lower bound in the sense that one have to use an exponential number of measurements to learn an arbitrary state. So that lower bound is there, and there's no way to surpass that. However, one can consider other problem. For example, we focuses only on physically relevant quantum states rather than all possible states. And then in those cases, this method could potentially provide a simple procedure for doing certification that only utilizes single qubit measurement. So one only needs to measure each qubit individually. And furthermore, if one go through the slides more carefully, if one go to the protocol, one can see that the protocol is, there's a very nice aspect of a protocol, which is no matter what we have in mind, we're going to do the same thing in the real world. So the experiments that we do is the same, irrespective of what we want to check between the real world and the model. And that's what we can do is we can collect a bunch of data, and now we just cycle through all kinds of possibility in our mind in order to check which one is closest using the data that we collected. And hence that provides a simple way to potentially do different kinds of quantum state tomography. However, so far we can only perform pure state tomography, that is to learn a pure state, or maybe the real world is not pure because the real world is often mixed. But what we would do is we will learn the closest pure state that represent the real world. But as of now, the current method wasn't able to handle mixed state. So that's definitely another interesting open question or follow-up question to consider in the future.
Oh, okay, and yeah, I'll have fun trying to go over all that. Yeah, thanks a lot, and maybe another one is for application. Forgive me if you've answered this enough, but applications beyond search, you know, potential for optimization, simulation, machine learning, uh, seems to be. I mean, is that relevant? And also, if we can generalize this approach to more complex states, and just hopefully I'm not uh, I'm not being repetitive.
Yeah, no. Yes. So here it would not be like application of this approach to classical machine learning, but more like one can use machine learning combined with these new certification protocol to learn about quantum physics, learn about quantum systems, etc. This certification protocol can also be used for performing optimization of quantum circuit. So we have we want the quantum circuit to prepare certain state to generate certain complex states. Then we can use this protocol for. And finally, for can we use this for complex states? So yes. So the main theorem that we proved in this work is that for almost all state, even if it's exponentially complex, we can utilize this certification protocol for checking whether the state in the real world is close to the state we wanted to prepare, and hence this also works in that region. Yeah. Thank you for your questions.
Oh, okay. Yeah, yeah. So the only other thing I can think of is so it exploits near-term and early fault, tolerant quantum computers is the only thing, other thing that came to mind. And thanks for all this. I can't wait to go over all this.
Yeah, thank you so much.
Yeah, thank you, Kevin. So maybe there's still more time to ask a few questions. So there's a question also from my other group. Are there any known limitations or edge cases where this protocol might fail or provide less accurate results? Did you find some opportunity to check this out in your study?
Yeah, so at the final slide in the Google Drive, I listed this open question. Basically, ask: are there states that are not certifiable with few single qubit measurements? So here we proved that almost all states can be certified, but we didn't prove that all states can be certified, which is a little bit it's still different. So right now we don't really know. So that's the best answer I could give. Hence, there's this open question listed in the last slide. We don't know if there's any state that cannot be certified with few single qubit measurement. Um, Not even candidate one. So originally we were playing with some code state like quantum error correcting code. Those states are known to have very intricate and protective entanglement that makes it very hard to extract the information contained in them. And hence, one might expect that maybe they're hard to certify. But it turns out it's not the case. All quantum error correcting codes can be certified with few single qubit measurements. So from that, it's a little bit unclear to us what would be the situation where there are states that are not certifiable with few single qubit measurement. And also note that, however, if we focus on the simplest protocol, like the one that explicitly the one that I presented right now, I think maybe there are, but there are simple ways to slightly enhance it, which are also discussed in the paper. In the paper, we discussed like a family of protocols that inspired by this, that are very similar to this, and they're slightly they can be more powerful. And if we consider that stronger family, that more encompassing family, then suddenly we don't know of any example where the states cannot be certified using few single qubit measurement. So that remains to be an open question that hopefully one could answer in the near future.
Yeah, thank you, Robert. So there are comments about using it in fields outside of quantum computing, such as cryptography or condensed matter physics. Yeah, I'm sure you know that there are other use cases. So when you find out next time, if you have a next paper, please you should be a regular guest speaker here.
Yeah.
So we have Lisa who came on stage. Lisa, hi.
Hello, thank you. Yeah, I wanted to ask a question actually about the comment that you just made, which is cryptography. And there are people worried about quantum computing systems breaking cryptography, and it seems like this would offer a way to do, verification and possibly zero knowledge proof type things. So I was wondering, what your thoughts are on applications in that area.
Ah, yeah. So that is a interesting angle. I also felt like there could be crypto related applications of the certification task because oftentimes in a learning algorithm can learning and crypto are essentially the opposite side of the same coin. If something can be efficiently learned, something can be efficiently seen, it means that they cannot be secure against attack. So if something are hard to learn, something cannot be are hard to see, then they're equivalent to they're essentially cryptographically secure. And hence there's always this very deep and foundational connection between learning and cryptography, and hence it does felt like this new protocol for how to see entanglement in quantum systems using these very simple local measurement might have applications to better understanding of quantum cryptography. However, as of now, I'm not a crypto expert, even though I work a lot on learning. I don't fully understand what kind of things people want in crypto and how this these new learning development could be applied there. So I would have to wait until some quantum cryptographer picks out some of this work and tell me about some of their follow-up results on it. So as of now, I don't really know, but I do see promise in that area.
Thank you.
Um, yeah, there's one more question here from Alpha. Uh, how does combining shadow overlap with neural networks enable the rigorous prediction of quantum system properties? Can you provide some kind of example? Or, yeah, maybe you had mentioned it earlier, but
Yeah,
also, yeah.
definitely. I could. I was a little bit quick on that front, so I could try to be a bit slower. So, so the idea is the following. So first, what neural network would do is essentially provides a parameterized family of quantum systems that it can represent, and so that's kind of what it does. And hence, by training them, we can explore that space. And then after certifying them, we will be able to make sure that the thing that the neural network, the state that the neural network learned, is actually close to the state in the real world. And after establishing that connection, we can now use this neural network to make predictions of all kinds of properties. And there are several very nice techniques based on kind of weighted Monte Carlo sampling that can be used to do this prediction of properties. And that was detailed in our paper. That's how kind of what the procedure looks like. But now let's go back to what kind of power does it bring? What new power does shadow overlap plus neural network brings? So note that shadow overlap only requires single qubit measurement, which measures each individual qubit um, locally. And it is well known in the literature that such a measurement strategy are quite limited in extracting properties in general. So if we just have an arbitrary quantum system in the lab, and now we can perform single qubit measurement. Now, if we wanted to extract some highly global properties, that's going to be extremely hard. One needs to perform like exponential number of measurements in order to extract those properties in general, when the state is arbitrary. And one example is actually the subsystem purity that I described in which I showcased in slide 76. In order to extract subsystem purity when the subsystem is like half of the system, then that is a well-known problem where when you only have single qubit measurement, that requires an exponential number of measurements in general. However, when one can train the neural network to learn the system, and if the neural network actually trained well, and then we can now certify it, and we can make sure that the neural network has trained well, and then we can use the neural network to make prediction about the subsystem purity very efficiently. And hence, it says that whenever there's so now what it says is the following. Even though in general, extracting subsystem purity from single qubit measurement is exponentially hard, if we can now use a neural network to represent, if the neural network has the ability to represent the quantum system, and it also has somehow maybe luckily, heuristically, can learn the system from the data it was provided to, then suddenly we get the power that, and then we can now certify it using shadow overlap. And now we have the power to estimate properties that are exponentially complex to measure originally. And that's kind of it's a little bit long process. So first we take the data, single-qubit measurement data. Now we use data to train the neural network. So the neural network tries to learn. And at the end, we use the shadow overlap to certify it. Now after we certify it, we know that the neural network is great, and then we use the neural network to predict some very complicated observable that are very hard to measure in the lab. So I think that's like one of the a key advantage or power of combining neural network and shadow overlap in practice. I hope that answers the question.
Cecilia, you're still muted.
Oh yeah, I guess she's muted. Well, maybe I have another question. For shadow overlap. For quantum error mitigation. You
Yeah.
know, it helps in recovering noiseless properties using a noisy quantum computer. Is that correct?
Oh yeah. Actually, that's a great point. So when we have a noisy quantum computer, it generates certain state. And then now what one could potentially do is like train a neural network to try to find the best noiseless representation, the best pure state, noiseless state that is closest to the noisy state that was prepared in the lab. And then we can use the neural network again to predict properties and so on. And hence, it provides a different way for performing error mitigation. So that could also be a potential. I haven't tested how well that performs, and is there any issue with that? But it sounds like a very reasonable idea, and it could potentially work well in practice. That's a nice idea.
Yeah, thank you, Kevin. And I apologize. I was momentarily dropped out of the room, so I think there was some kind of silence. So anyway, yeah, we've been here for 1 hour and 30 minutes, and we'd like to ask Robert if he can take in more questions, or
Yeah,
shall
I think
we?
it's a little bit late in the place I am, so I might have to run quite soon. And thank you all for all the questions. It was great.
Yeah, thank you for coming here, Robert. And please know that you have many fans here in Quantum Photonics. We are all rooting for your success because the next time you will be Professor Robert, Professor Wang in
Thank
Caltech.
you.
So, yeah. Anyway, I'd like to thank everybody who are here, and I'd like to say hi to Eli, who is in the audience. We miss you, Eli. I'm sure you missed us also, but we haven't been here like we used to do every day. And we'd like to thank everybody who supported the room. Of course, Kevin and Lisa, and we have Ashsel, Kyle, V, Eli, Karen, who is from Facebook also, and Dell, and we have Drew, and yeah, I don't know if Blackbeard and Carlos. So thank you so much. I'd like to ask Bob before we give Darcel, who is supposed to be up here on stage. I will invite him to speak to help us close the room. I'd like to give the mic to my moderator, Bob, if you have something to say before we close the room, Bob.
Thank you so much, Bob.
Yeah, you know, Robert, when Bob first saw the slides just before we opened the room, he said, wow, 84 slides and very well explained. And he is the one who is trying to sync our slides with the recording. And he is very excited to do that
Thank
for
you.
the YouTube channel. Yeah. So, Darcel is not here yet, Bob. I think he can't go up.
Oh,
I'm
he's
here.
here.
I'm here, Cecile.
Eyes here. I cannot see you, so yeah, I'd like to give the mic to Darcel to help us close the room. And thank you once again, Robert.
Thank you so much for the invitation.
Yes, thank you, Doctor. That's future tense for you. um, to close the room, we're going to start our countdown from lucky number 6. Is everybody ready?
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 6.
Six,
Six.
Six.
Lisa Megawatt 5.
five,
Kevin Cuatro.
4.
Bob Trace.
Three it is.
Cecile Dos Equis.
Two.
Robert, good doctor, you're number 1. Call out our last number, please.
1.
Yeah. Thank you, Robert. Good night, and see you back
Thank
in
you.
Quantum Photonics. Yeah. Good night, everyone. See you in the next rooms.